Section 7.2 is volume, the disk method. Now, one application of the definite integral is that it allows us to find the volume of a three-dimensional solid. So let's talk about a solid of revolution. A solid of revolution is the resulting solid obtained when you take a region in the plane and you rotate it about some line, and we're going to call that line the axis of revolution. For example, if we look at this blue line all the way down to the x-axis, and we were to take this yellow region and then rotate this yellow region around the x-axis, we would obtain a figure that looks like this. Let me just draw it on this side right here as well. Again, if we take it and just revolve it around the x-axis, we would end up with a solid that looks like this. So one method that we can use to find the volume of a solid of revolution is the disk method. So we're going to look at the disk method and then the washer method a little later on in this section. Recall from geometry, we say that the volume of a cylinder is V equals pi r squared h. Given a cylinder, its volume is pi r squared for the area of that circle, and then h for the height of your cylinder. Now, if we were to look at this picture here in green and just take a cross section of it, so just take one little bit out of here and pull it right out, what we would end up with is a cylinder. So we would have this cylinder right here. Now, the height of this cylinder is that change in x, or that x movement, and the area here would just be pi r squared. Pi r squared again represents the area of that disk, and h represents the width of that disk. For the disk method, what we want to think of is if we were to stuff an infinite number of disks inside the solid of revolution, which would make the width of each one of those disks going to 0 to give us an infinite number of disks inside of that solid of revolution, we would be able to more accurately find the volume of that solid. So here's an example of us saying that what we could do is add up an infinite number of disks inside of that solid of revolution, but we know that this summation is just the way that we got to the definite integral in Calculus 1. Therefore, we say that we can use this formula right here to find the volume of the solid of revolution. So the volume is going to equal pi times the integral from a to b of r of x squared dx, where r of x is the radius of the disk. Now please note that the radius is always going to be perpendicular to the axis of rotation. So it's always going to be perpendicular to that axis of rotation. The other thing that you should note is that it's going to be the distance from the curve to the axis of revolution, or that axis of rotation. We have two possibilities for lines that we revolve around. We have horizontal lines we'll be revolving around, so we're going to look at a horizontal axis of revolution, and we're going to look at vertical axis of revolution, or revolving around a vertical line. When you have a horizontal axis of revolution, for example, if we're revolving around the x-axis because the x-axis is a horizontal line, we are going to integrate with respect to x. So if we were to draw the same region we had before, this region right here from A to B, and we were to rotate this yellow region about the x-axis, the radius would be the distance from the curve to the axis of revolution, and that radius has to be perpendicular to the axis of revolution. This would be the radius, or r of x in this case. For a vertical axis of revolution, so let's call this here C and this here D, and just draw in the region first. So if we were revolving this yellow region about the y-axis, because the y-axis is a vertical axis of revolution, our radius is still going to be perpendicular to the axis of revolution. And when we have a vertical axis of revolution, we have to integrate with respect to y. So for both of these, your radius is going to be perpendicular to your axis of revolution. And for both of these, the radius is going to be the distance from the curve to the axis of revolution. The only difference is if you have a horizontal axis of revolution, you integrate with respect to x, which means everything in this integral has to do with the x-axis or a function of x. And if you have a vertical axis of revolution, everything here has to do with the y-axis or a function of y. Let's look at some examples where we're finding the volume of the solid generated by revolving the region bounded by the graph of the equation about the given lines. Number 1 is y equals the secant of x, y equals 0, x equals negative pi over 4, x equals positive pi over 4 about the x-axis. Now we don't need to draw this, but I'm going to go ahead and draw it so that I can figure out what is my region so I can find my limits of integration and my radius. If we were to draw this, we know what y equals 0 looks like. That's just the x-axis, so here's y equals 0. We know what x equals negative pi over 4 is. That's just a vertical line, so here's x equals negative pi over 4. And we know what x equals positive pi over 4 is. Again, just a vertical line. Here's x equals positive pi over 4. Finally, let's draw in the secant of x. Well, we can just use numbers to draw the secant of x. When x is negative pi over 4, the secant of negative pi over 4 is going to be positive square roots of 2. So let's just put a dot here at the square root of 2. When x is 0, the secant of 0 is 1. So let's put a dot here at 1. And finally, when x is positive pi over 4, the secant of positive pi over 4 is the square root of 2. So that's the other dot. And we're going to connect those dots. And there we go. Our region is this yellow region right here, the region that's trapped by y equals 0, y equals the secant of x equals negative pi over 4, and x equals positive pi over 4. Now let's see where we're rotating it about. Well, we are going to revolve it around the x-axis. Well, the x-axis is horizontal. Since it's a horizontal axis of revolution, we know that we're going to need to integrate with respect to x. Now, instead of writing integrate with respect to x or integrate with respect in general, you'll see me write I, W, R for integrate with respect, and then I'll say to and whatever variable. So horizontal axis of rotation, I know I need to integrate with respect to x. That means that my limits of integration from a to b have to be an x, and that my radius has to be a function of x. Let's first figure out if we can see what the limits of integration are. Do I have a bound to the left and to the right on my x-axis? Absolutely. This is the leftmost I go on that yellow region, and this is the rightmost I go on that yellow region. My volume is going to be pi times the integral from negative pi over 4 to positive pi over 4. Now I just need to figure out what my radius is. Recall your radius is the distance from the axis of rotation to your curve, and your radius has to be perpendicular to your axis of rotation. Well, this right here would be the distance from the axis of rotation to the curve, so that's my radius. Well, what is that? Well, that is just going to be the curve itself, this black curve, which was the secant of x, going all the way down to that axis of rotation, which is the x-axis, or y equals 0. So I'm going to say minus 0. So your radius is just going to be the secant of x. You don't need that minus 0. Here we're going to have our radius, which is the secant of x, quantity squared dx. Because remember, your disk method is always going to be volume equals pi times the integral from a to b of your radius squared, and it's either dx if you are a horizontal axis of revolution or dy if you're a vertical axis of revolution. Let's go ahead and integrate this and finish off this problem. Well, can I integrate secant squared? Yeah, if it's weird to you that way, you can always rewrite it as the secant squared of x, and that's just going to be basic form. We know that the integral of the secant squared of x is the tangent of x, and then we're evaluating that from negative pi over 4 to positive pi over 4. Plugging in those limits of integration, tangent of pi over 4 minus the tangent of negative pi over 4. Well, the tangent of pi over 4 is 1, and the tangent of negative pi over 4 is negative 1, so my volume would be equal to pi times 1 plus 1, or 2 pi. Let's look at our second one. Our second one is x is equal to negative y squared plus 4y, y equal 1, x equals 0, and we're going to rotate this about the y-axis. Well, the y-axis is a vertical axis of rotation, and since it's vertical, I know I need to integrate with respect to y. So my limits of integration have to be in y, and then my function has to be a function of y. Let's go ahead and graph everything so I can find my region, to find the limits of integration, and to find the radius. If I were to graph this, well, I know how to graph y equal 1 and x equals 0. That's pretty easy. The one I might have a little bit more trouble with is this x equals negative y squared plus 4y. Well, I know that that is a parabola. Since y is squared and it's negative, I know that it opens left. I know that it's going to cross the y-axis, so the y-intercepts are going to happen when x is equal to 0, and those are going to be, well, if I factor out a y, at y equals 0 and at y equal 4. If I wanted to, I could complete the square to find the vertex of this parabola, just so that I could also have that to graph. So let's just practice completing the square to find the vertex of this parabola. So I'm going to take this and complete the square. So we say x is equal to, have to factor out the negative, y squared. Since I'm factoring out a negative, that becomes a negative 4y. And then we add a blank there. But remember, there's a negative in front of it, so I'm not really adding, I'm subtracting. So the opposite of subtraction is addition. Bring down that negative, and then open an empty set of parentheses and hit squared. The variable that I'm dealing with inside these parentheses is y, and then half of a negative 4 is a negative 2. A negative 2 squared is a positive 4. That's the number that goes into these blanks. And then we have x equals the negative of y minus 2 squared plus 4. Moving this guy over with x, I have x minus 4 is equal to the negative of y minus 2 squared. Well, the vertex there of this parabola is going to be, well, the number opposite with x is 4, and the number opposite with y is 2. So our vertex is 4, 2. We're going to graph all of this so we can find our radius and our limits of integration. Let's start by graphing this parabola. Again, its vertex is 4, 2. It crosses the y-axis at 0 and 4, and I know it opens left, so it looks like this. Then I'm going to draw y equal 1. Well, y equal 1 is just this horizontal line. And then I'm going to draw x equals 0. Well, x equals 0 is just this vertical line. The region that's trapped by pink, orange, and blue is this region right here. And we're going to take that region and we're going to revolve it around the y-axis. So we're revolving that yellow region around the y-axis. I need to look at this and determine what are my limits of integration and what's my radius. So I have b equals pi times the integral. Well, can I see the limits of integration? Do I see what my smallest y value for this yellow region is? And what my largest y value for this yellow region is? Absolutely. My smallest y value is y equal 1, and my largest y value is y equal 4. So I have to go from 1 to 4 of radius squared. Now remember, your radius is always perpendicular to your axis of rotation, and in this case, because our axis of rotation is vertical, it has to be a function of y. This right here would be my radius. Well, what's this radius? Well, it's the distance from the pink curve to the orange curve. So in this case, the radius is, and the pink curve was, negative y squared plus 4y minus, well, the orange curve is 0. Cleaning that up because I don't need my minus 0, and I get that my radius is negative y squared plus 4y. So this is going to be negative y squared plus 4y quantity squared dy. Now it's time to find this volume, so I need to first square negative y squared plus 4y. If you need to, go ahead and write it twice so that you can FOIL, just to make sure that you are multiplying this correctly. Well, if we were to square this guy, well, we would have positive y to the fourth and then minus 4y cubed minus another 4y cubed is minus 8y cubed, and then finally plus 16y squared. Now that I've distributed, it's time to integrate. So I end up with pi, and then this becomes y to the fifth over 5 minus, if I divide this by 4, it becomes 2y to the fourth plus, and then 16y cubed all over 3, and this gets evaluated from 1 to 4. Plugging in those limits of integration, we have 4 to the fifth over 5 minus 2 times 4 to the fourth plus 16 times 4 cubed over 3 minus 1 to the fifth over 5 minus 2 times 1 to the fourth plus 16 times 1 cubed over 3. Plugging that into a calculator, we would have alpha y equals for a numerator and denominator, and then it's 4 to the fifth divided by 5, and then minus 2 times 4 to the fourth plus alpha y equals for a numerator and denominator 16 times 4 to the third divided by 3. And then I'm going to go ahead and say minus and open a parentheses here for the second one. And since it's just 1 to the fifth, I'm going to go ahead and just write 1 over 5 instead of 1 to the fifth over 5, because we know that 1 to the fifth is just 1. And then instead of 2 times 1 to the fourth, I'm just going to say minus 2, because we know that 1 to the fourth is just 1 times 2 is just 2. And then the last one, following the same pattern, we're just going to go ahead and write 16 thirds. So alpha y equals, and then we're going to put in 16 thirds, close our parentheses, and we end up with 153 over 5. So my volume here is 153 pi over 5.